In this video, we're going to look at reductions of benzene. Now, as with other alkenes, we can treat benzene with hydrogen gas in the presence of a catalyst to get it to completely reduce to cyclohexane. It's possible, although it's kind of pointless. You're really removing every sense of functionality that your compound once had by completely reducing it to cyclohexane, but you could if you wanted. It's kind of not so synthetically useful, but it is possible. Note that because this is an aromatic compound, we're removing its aromaticity. We are still lowering its energy by reducing it, but the reaction conditions are pretty extreme. 100 atmospheres of hydrogen, that's a bomb. That's extremely explosive. You're really setting up a bad time there. Of course, again, this is really just something more theoretical. It's not very often done. It is not often that you want to remove the reactivity of a portion of your molecule, but you can. It should be noted that with certain catalysts, you can reduce other groups in the presence of a benzene, but they're not, again, terribly useful, because reductions tend to be removing our at least of multiple bonds. They remove reactivity, and so it's kind of like we can't do anything now. We spent all this time getting these things to be reactive, and then you turn it into an alkane and can't do anything anymore. So, suffice it to say, though, there is one reduction that is particularly useful, and that is the birch reduction. And in the birch reduction, we're going to start with the benzene. We're going to treat it with sodium metal, methanol, in liquid ammonia. Liquid ammonia means specifically it's going to be a very cold reaction. We want it to be thus because sodium would react with methanol otherwise. But we also want to control what's happening here. And so this is typically a very cold reaction. And what happens here is we end up removing just one of the double bonds. And we end up with two non-conjugated, two isolated double bonds at opposite sides of what used to be benzene. So we end up with a 1,4-cyclohexadiene, which still has quite good functionality, right? We have now two alkenes. We can do things with those. We can turn them into epoxides, do other fun stuff, or use them in Diels-Alder reactions that we wouldn't normally be able to use benzene with, but we could do a Diels-Alder with a cyclohexadiene, even if it's 1,4. It, of course, would have to be the dienophile, but it could be done. Let's take a look at the mechanism here. So when we're looking at benzene, of course, benzene has 6 hydrogens. And if we look at our final molecule, of course, it has 8 hydrogens, right? It's got the 4 on the double bonds and then 4 on sp3 carbons there. So what's going to happen here in the first step, just like with alkyne reductions, remember we use sodium and ammonia to make a transalkene out of an alkyne? The first step here is we're going to have a sodium electron add to our molecule. Notice that I'm using the fishhook arrows here, one side only, because this is a radical, 1 electron. That's going to cause the following set of reaction arrows to happen. We're going to end up breaking one of those double bonds, forming a new double bond here. This is our new double bond. New double bond there. We're going to end up breaking another 2 double bonds, forming one new one. And if we follow the arrows, what we're left with at the end of this step is we have an anion now at that top position. We have formed a new double bond on the side, and we have a radical at the bottom. So we see here that those two blue arrows on the left, right, like the leftmost ones, those two are forming the new double bond. That's the new double bond that's going to be forming right here along the left side of the molecule. Because those double bonds with the blue arrows coming out of them are being broken. And so we're left with a radical anion. So we have a radical on one side and anion on the other. Just like before, we have our proton donor, our solvent in this case, or rather the methanol. So our lone pair is going to grab one. Notice now we have a double-headed arrow, because this is a 2-electron process. So we will end up losing a methoxide ion. We've also lost a sodium ion technically here. We've lost a methoxide ion now. But we've added on a hydrogen now. We have our two parallel double bonds, and we still have our radical at the bottom. It still has one hydrogen on that carbon as well. So, process repeats itself. Here comes a sodium atom. It's going to go ahead and donate its electron, singular, onto that position. As a result, we have now a lone pair down there with a negative charge. It's going to go ahead, just like before, and find a methanol. And we're going to go ahead and again, in a 2-electron process now, grab one of those protons. Oops. And as a result, we will end up now with our reduced benzene. So just like before, in some of these steps, we're going to lose more ions. Those are byproducts. We have lost our methoxide and our sodium ions. But we have now fully reduced, or rather, fully partially reduced. We've completed our birch reduction, suffice it to say. We have ended up with our benzene. And so if we want to consider what happened in this mechanism, note at both sides where that reduction is taking place, where the hydrogens are being added to the molecule, those are at the top and the bottom, and it proceeds through an anion pathway. And so we want to think, what's going to help stabilize this? So, because the mechanism proceeds through an anion intermediate, if we want to look at factors that might stabilize that anion, we could think, okay, well, what's going to help stabilize it? Well, if we have an anion, that means we have too much electron density, right? We have a lone pair on a carbon. That's not a very good thing, right? So things that will stabilize it would be electron withdrawing groups. So something like putting a carbonyl on there, acetophenone, when we reduce this, we end up reducing specifically at that position. So we are going to reduce at the position to which our electron withdrawing group is bound. So notice this is the reduced carbon is bound to the electron withdrawing group. And of course, because the mechanism has it such that we're going to end up with parallel double bonds, the side on the other part of the molecule will also be reduced, right? Because both things have to be reduced here. And so if an electron withdrawing group stabilizes it and allows that position to be reduced, we're going to see that electron donating groups destabilize. And so if we have an electron donating group, say we have a methoxide there, if we employ our reaction conditions for the birch reduction, we're going to see that we do not get reduction at that position. This molecule does not form. Instead, what ends up forming is we'll end up making our reduction happen at a different position. What actually happens under those same reaction conditions is we end up reducing at a different position. Notice we still have the same pattern. We're going to end up with parallel double bonds, isolated ones. We're going to have sp3 hybridized carbons on opposite sides of what used to be our benzene. But notice that the position, this carbon adjacent to the donating group is not reduced. So we'll reduce a different position. Doesn't matter which other position we reduce, it's just got to be one that's not bound to that electron donating group. And as a result, we're going to end up with having that reduction take place on a different carbon, one away from the one to which the donating group is attached. With the electron withdrawing group, it's going to happen there. It's going to be reduced at the position to which your electron withdrawing group is attached. In the case of having an electron donating group, we see it not on that carbon. And so the carbon that holds the electron donating group will still be part of a double bond. It's not going to participate in this mechanism. And so we're not going to see it being reduced as a result, because it's donating electron density. That's going to destabilize having a lone pair there. Remember that the intermediate would be putting a lone pair right next to an electron donating group. That's a site of electron density right next to another site of electron density. Those clash. Not a good thing. But if we take a look at the electron withdrawing group, if we look at its intermediate, we can see, in fact, it's resonance stabilized. We can, wow, that's terrible. This is way too small of a molecule, but it's resonance stabilized. So it actually stabilizes that position, allowing this reaction to happen more easily. So the point is, when you have an electron withdrawing group, you will try and reduce that carbon, the one to which your electron withdrawing group is attached. If you have a donating group, even something like a methyl group, that's a donating group, we will try and reduce a different carbon, reduce something else. So notice how we've reduced one to the side. Doesn't really matter which one, as long as it's not the one directly attached to the donating group. And so, with the birch reduction, you can selectively decide where you want those two double bonds to show up by placing your substituents on appropriately. And so, in our next set of videos, we're going to study, instead of now reduction or benzylic reactions, we're going to study actual reactions substituting onto the benzene itself. And it'll be plenty of reactions. We'll have a lot of fun with it. So we'll see you then.